Hello, good afternoon, everyone. Okay, so today we're going to continue with what we started last session. So last session we focused on the one-way ANOVA, and then we did a number, at least 3 problems involving one-way ANOVA. So just by recap, the study of ANOVA is part of this set of procedures that deal with testing whether 2 variables are independent or not. Okay, so the ANOVA that you see here is used when the dependent variable is something that's measured, quantitative, and then the independent variable, or also known as the predictor variable, is qualitative, okay, so meaning categorical. So by way of starting the ANOVA example, especially in the one-way ANOVA, and we defined the one-way ANOVA is where you have one quantitative response variable and one qualitative predictor variable, all right? So by way of starting the discussion on this topic, we asked for, we used the class as an example for those who were present when I collected the data, representing the heights of the men in the class versus the heights of the women in the class. All right, so you'll note here that the variable, the response variable, which is height in inches, is quantitative, meaning that's measured, whereas the predictor variable is gender of the student. Okay, gender is a classification or qualitative variable. So in this example, we talked about that a one-way ANOVA, actually, especially if you are comparing means of 2 groups, is the same as conducting a 2-sample t-test, assuming equal variances from the previous chapter that we discussed. So today we are going to talk about ANOVA, but this time we will deal with what is known as a 2-way ANOVA. All right, so what is a 2-way ANOVA? Again, a 2-way ANOVA is where you want to compare means of groups where the response variable is measured or quantitative, but this time, instead of just having one qualitative predictor variable, we will have 2 qualitative predictor variables. So as far as the one-way ANOVA is concerned, the 2-way ANOVA is concerned, if you look at the template for this procedure, we dealt with the one-way ANOVA, a number of problems last session, and then we used this last item, the 4th template, in comparing the variances or standard deviations of 2 groups. So for the 2-way ANOVA, we will be looking at this 2-way ANOVA with replication, and I will explain what that means, and then 2-way ANOVA without replication. All right. Now, let's look at the hypothesis setup for the 2-way ANOVA with replication and without replication. So over here. So the first part B talks about 2-way ANOVA without replication. Now, this kind of analysis breaks down into 2 specific hypothesis tests. One is the testing for main effect, and then the other one is testing for the blocking variable. All right, but you will note here that the hypothesis set up for testing the main effect, treatment A or treatment B, note that this hypotheses are the same as the way we set up the one-way ANOVA. That is, we will state the null hypothesis. that the means of the groups in whatever treatment or the factor, they are all equal. All right. Another interpretation of the null hypothesis is that no level of factor A has an effect. All right. So this is similar to when we do hypothesis testing in the one-way ANOVA. All right. So when we talk about, let's see, let me see if I can find another, yeah, like this here. That when we say that the means of the groups are all equal, essentially we're saying that the variable, whatever the response variable is, and whatever the factor or the predictor variable is, that they are independent. Alternatively, when the null hypothesis is rejected, then we're saying that, variable 1 and variable 2 are dependent, meaning one affects the other. So this is another way of stating that dependence or independence between two variables. The decision rule will still be the same, where we compare the computed F to the critical F. All right, so this is nothing really new. The only difference is that you will now have two factors. All right, so let's look at an example in how we conduct this two-way ANOVA without replication. All right, so here's the example, 1239. Shanks Incorporated, a nationwide advertising firm, wants to know whether the size of an advertisement, okay, so that is the variable of interest. I'm sorry, not the variable of interest. One of the factors, size of the advertisement. And the other factor is the color of the advertisement. Okay, so you'll see over here, this is one independent variable, the color of the advertisement, and then on this side, you have the size. So this is factor 1, this is factor 2. And note that both factors are categorical. So they want to see if size and color make a difference in the response of magazine readers. All right, so what is this response? Each reader is asked to give the particular combination of size and color rating between 1 and 10. So, they're given a combination of a size and a color, and then the reader is asked to rate from 1 to 10. So for the combination small red, the reader gave a rating of 2. Okay, so these numbers that you are seeing in this table, these numbers here, these are the ratings assigned by the reader. And ratings is the response variable or variable of interest. Okay, so far? And ratings are quantitative. All right? So, going back to the question 1. What is the response variable? We just defined that as the ratings assigned by the reader, and the rating is from 1 to 10. Okay, and rating is some form of measurement, So this is quantitative. Second question, what is or are the factors? We have two factors, which we defined as the first one is the color of the advertisement. Okay, and there are three levels. So for X1 has 4 levels, and the levels are red, blue, orange, and green. Okay, the other factor is X2, and X2 is the size of the advertisement. And size of advertisement is also qualitative. Let me complete this. This is also qualitative. Okay, so how many factors are there in X2? There are 3. And the 3 levels are small, medium, and large. So in this, the way that this cross tabulation is set up, the treatment that we're really interested in is the color of the ad. All right, we want to see if there is a difference in the ratings by the reader based on the color of the ad. The size of the ad that you see here is known as a blocking variable. All right, and what is the use of a blocking variable? Well, a blocking variable is used to control the variability. So a blocking variable is a group of similar units, like this one, the small, all right, similar unit for the different colors. And blocks are used, the purpose of the blocks are to reduce the known sources of variability. In other words, when we conduct the test of hypotheses, comparing the average rating of the advertisements based on color, that we are actually controlling for the variability by using the size of the ad. All right, so there are, we cannot attribute sort of the variability that we observe to any other source. So let's talk about this, and what we mean by two-way ANOVA without replication. Now, this particular example is a two-way ANOVA without replication. Now, we can determine whether you're given a two-way ANOVA with or without replication, depending on the number of observations that you see for each combination of factor A and factor B level. So for instance, there is only one observation that you see here for the combination of red and small, okay? If you have 2 or more observations in each combination of factor A and factor B level, then we're dealing with what is known as a two-way ANOVA with replication. Okay, so let's look at an example, and I'll go back to this, just so that we can see the difference between a two-way ANOVA without replication and with replication. We will solve this problem shortly. If you look at this problem here, all right, now in this table, you'll see 2 factors, sector and then gender. And for each combination of sector and gender, you have multiple observations known as replicates. So for example, combination of these are accounting, I think accounting employees in the public sector who are men. There were 5 individuals that fell within this category. So this is an example of a two-way ANOVA with replication. Okay, does that make sense so far in terms of the difference between two-way ANOVA without replication and two-way ANOVA with replication? Okay, good. All right, so this is, we said this is a two-way ANOVA without replication. And when you have this, the hypothesis setup is, boils down to a test of hypotheses of, the treatment A and the blocking factor. All right, so we'll set up the hypotheses. Factor A, and this factor A is the color of the ad. All right, so factor A is color of the ad. So the null hypothesis would be, the null hypothesis would say this: H sub 0, the average rating using red, okay, of the ad is equal to the average rating of the ad that is in blue, is equal to the average rating of the ad that is in orange, and which is equal to the ad in green. Okay, translation. The color of the ad has no effect on the rating. Translation, a consumer reading an ad will rate that ad regardless of the same. We'll rate that ad the same way regardless of color, right? Or the other way we express this, as we did in the one-way ANOVA, is that we will say that the color of the ad and rating are independent, meaning the color of the ad does not make any difference in terms of how a consumer or a customer will rate the ad. The alternate hypothesis will be written this way, in the same manner as we did in the one-way ANOVA. At least one of the means is different. Okay, translation of these this alternative hypothesis: the color of the ad has an effect on the rating, or the color and rating are dependent or are correlated. So that's the factor A. Now, how about for factor B? Well, for factor B, the factor B, which is the blocking variable, is the size of the ad. All right. So we state the null hypothesis for factor B. H1 or H sub 0, the mean rating for small is equal to the mean average rating for the medium is equal to the average rating for the large ad. Okay, translation, the size of the ad has no effect on the rating. And for the alternate hypothesis, we'll say that at least one of the means is different. Okay? So once again, a two-way ANOVA without replication, this one here, reverts back to two tests of one-way ANOVAs. That's what we see down here. Okay, so this is a one-way ANOVA, and this is a one-way ANOVA. So the decision rule will be the same as before. We will reject the null hypothesis if the computed F is greater than the critical F, or if p-value is less than the significance level. All right, so now we're ready to generate the computed F or the p-value so that we can render a conclusion of these two-way ANOVA. So are we clear so far? Good? All right. So let me copy this data. And I'm going to move this away so I can copy them. All right, Control copy. And then let's go to the template where we will be using two-way ANOVA without replication. Select that. And here you go. I'm just going to paste what I copied, the response variable data. Okay. And I'm going to replace the labels. So this is small, this is medium, and large. And this would be, I think, correct me if I'm wrong, red, blue, orange, and green. Okay, that's correct?
That's right.
That's the data. And what is this significance level? Is it given in the problem? It's not given in the problem. So let's just assume, let's just use alpha of 0.05. All right. So that's what we have up there. And so we scroll down, and here is the output that we will need to render a conclusion on those two hypotheses, pairs of hypotheses. Okay, so here's the output. Okay, so I'm just going to paste that down here. So as far as the what is the computed F? So for the treatment, let's see, treatment which is the color of the ad. The computed F is equal to, so here's the treatment. The computed F is this, 5.88235. And then the critical F along that same row is 4.7571. Okay? What's the p-value? The p-value associated with that row, the treatment, is 0.0321. And then for the blocking variable, which is the size of the ad, the computed F is 7.588. And then the critical F is 5.1433, and then the p-value is 0.0227. Okay, we're good so far? So if we simply just look at the p-values associated with treatment and then the blocking variable. So for the treatment, the conclusion would be to reject the null hypothesis. Okay? And then for the blocking variable, we will also reject the null hypothesis. And that is at 0.05 significance level. The interpretation of these two here. For the treatment, we will say that at least one of the average rating of the callers is different. Okay? And then for the blocking variable, we will say that at least one of the callers, the average rating of callers is different.
Did you mean add size on that second one for the blocking?
What did I say? Oh, thank you. Size. Thank you. All right. So this conclusion here begs the question, which color will you use? Which color will you avoid? This one says, which size would you use? Which one would you avoid? Obviously, you would want to pick a color or size that provides the largest rating. Right? We're assuming here that the higher the rating, the better it is. So let's go back to the output here. And you can look at the summary statistics here, which also gives us the confidence intervals that in terms of size, The worst one is the small. Okay. Why did I say that worst rating? If you look at the average rating, there's quite small. Which one has the best rating? Well, the best rating actually is, it's almost, I mean, there's big overlap between the medium and large. So you can do a two sample test and see if these differences are significant. Okay. In terms of the color, the best one would be, let's see, the green. All right. Are we good? All right. So that's problem 1239.
Can I ask a question?
Sure.
Just for, would you please scroll up to the top of the problem itself?
Mm-hmm.
So this business of treatments and blocking, it looks like anything along the top row is going to be the treatment, and anything in the column would be the blocking.
No, the row, the small, medium, large would be the blocking variable. The columns, the color of the ad is the treatment. Uh-huh.
So say, for example, in this question, we were given a question that did not have a table given to us.
Uh-huh.
And we set this table up the other way so that we had the size of the ad going across the top and the color of the ad going down.
Uh-huh.
Would that still render the same decisions and same conclusions as
Yeah,
long as
it
we
will.
set it up?
It will, yeah, because the these two hypotheses here are really independent.
They would just switch, so.
Correct.
Just,
The conclusions
okay.
will still be the same.
Okay, thank you.
Mm-hmm. Okay. All right, so let's look at 1241. 1241. The city of Tucson, Arizona employs people to assess the value of homes for the purpose of establishing real estate tax. The city manager sends each assessor to the same 5 homes. So you're talking about this, which is the blocking variable, then compares the results. All right, so the 5 or the 4 individuals here are the assessors. The information is given below in thousands of dollars. Can we conclude that there is a difference in the assessors, so meaning the average assessment made by each of these 4 assessors? We will test that at 0.5 significance level. Okay, so what is the response variable? Meaning, what do these numbers represent in this table?
Is it the value of homes?
Uh-huh. Value of homes assessed, as assessed, right? And this is in dollars. So this is quantitative. What are the factors? Okay, I'll start with treatment. What's the treatment here? Also known as the factor A.
Would that be the assessor?
Okay. Good. And this is qualitative, right? And then for the blocking variable, factor B,
The home?
home, okay, which is also qualitative. How many factor levels are there? For treatment factor A, there are 4 levels, which are the assessors. For the blocking, 5 homes. So since we have 2 factors, A and B, then this requires the two-way ANOVA without or with replication. Which one applies to this problem?
Without?
Okay, without replication. All right. And then we state the null and alternate hypotheses for treatment assessors. The null hypothesis would state that H1, HO, the mean of, we'll just denote instead of spelling out the names. So Z and CH. Mean for Z is equal to the N, mean of C, and the mean of H. All right. Obviously, if they are assessing the same home, we would want the same assessment, right? So for this, we would want to not reject the null hypothesis. So another interpretation of the null hypothesis is this: no difference in assessment by the 4 assessors. Meaning we want them to be consistent in assessing the same kind of home. Do you agree? Okay. H1, at least one assessor has a different assessment average. Okay. In the same manner, when we look at the different homes, the 5 different homes, so the homes, we would want the averages to be the same also regardless of the assessor. So the null hypothesis would say that the average assessment of home A is equal to the average assessment of home B is equal to the average assessment of home E. Okay? So translation, no difference in average assessment values of the 5 homes. The alternate hypothesis that at least one of the home homes has a different assessed value. So the decision rule will be, again, using this here. I'm just going to copy this down. Oops, I need. All right. So we will reject the null hypothesis if the computed F is greater than the critical F, or if the p-value is less than alpha. So let me copy this information, go back to the template, paste the data here, and here's the output that we will need. Okay? So the computed F for the assessor is equal to 0.66823. It's quite small. And the critical F is 3.4903. And the p-value is, again, it's quite high. Okay, and then for the house, the home, the computed F is equal to 100.20203, and the critical F is equal to 3.2592, with a p-value of almost 0. So for the statistical conclusion, we'll say the average assessed value of the homes is the same for all 4 assessors. Okay? And again, we want that. We want the assessors to be consistent in assessing the values of the same type of home. But when it comes down to the assessed value of the homes, regardless of assessor, we rejected the null hypothesis because the computed F is greater than the critical F, or the p-value is a lot smaller than the alpha. Then we will conclude that the average assessed value of the homes is not the same regardless of assessor. Meaning one of the homes is valued differently, or at least one of the homes is valued differently. Which one is that home? All right, as far as the treatment of the homes, or the average of the homes based on the assessor, they're the same. Practically these are the same. We'll say not different, but in terms of the homes, which of the homes do you think is or are value assessed differently? These first three homes are about the same. Right, the range is between 40,000 and 57,000. But if you look at these two homes, they're valued differently. Does that make sense, though? All right. At least why these two homes are valued differently. No, because maybe these two homes have different characteristics than A, B, and C. All right. So it may make sense for them to have an average assessed value. But as far as maybe this the manager of this what is this yeah, the city manager, as far as this person is concerned, he or she would want consistency among the assessment by assessors. All right. Does that make sense? Okay, good. All right, one more. Why don't you do this on your own? I'll give you, 5 minutes. So identify the Y, identify X1 and X2, and then determine the number of factor levels, set up the null and alternate hypothesis, the decision rule, and then complete these 7, 8, and 9. And for this problem, we're going to solve this using the data analysis module of Excel instead of using the template. Okay, so one of the options in the data analysis is this analysis 2 factor without replication. So you can also solve this problem using the data analysis module of Excel. All right, so I'm going to be calling on students now, right? So we have other students participating. As far as number 1 is concerned, Grace.
I think it's the number of miles driven.
I'm sorry?
This is for number 1, right?
Yeah.
Okay,
what is the response variable?
Is it the number of miles driven?
Right. Number of miles driven. And then this is quantitative. Good. Factor. Okay, David, you're there. I see you.
Is it the type of car and the type of gas?
Okay. Yep. So X1 would be the let's make this clear that this is the treatment. All right, which would be the type of gas, and the way this is also a qualitative variable, and then you said X2, which is the blocking. What was that you said, David?
The car, like car A, car B, car C.
Okay. Okay. We kind of reverse this, and let's see the column.
I was just going to say, isn't that the other way around?
Yeah. So I'll just replace this with 1 would be the car type, and then this would be X2. All right. This is also qualitative. So how many levels are there for the treatment?
There's 3.
Okay. For the block, you said, was that Iridium or?
No, it's Hannah.
Oh, Hannah. Okay, I said 3. Okay.
Yeah.
And then they are the different. Let's see. Did I mess it up?
Are you saying the treatment is 3, the car A, B, and C? Or using
Well, yeah, treatment is car A, B, and C. Let me fix this because I think I'm messing this up because of my. So X1. Let me fix this first, okay? Car type. All right, that's good. This is X2 is the gas type. Okay. All right, so I think this one is correct. All right, so treatment, car type, there are 3. And then block, the type of gas, there are, were there 5?
4.
It's 4.
Okay. Thank you. Okay. So for the null hypothesis, for the car type, okay, what will be the null hypothesis? Shania, you're there?
Yes. Is it going to be the HO equals the mu1 equals 2 equals mu3 equals mu, oh, just equals mu3, I believe.
All right, good. So we can just write this out in textual form. Say the average gas mileage of the 3 cars is the same, right? And H1 will say that at least one of the car types has a different average mileage. Good. And then for the gas type, the null hypothesis. James, are you there?
Yeah.
Okay. What's
So that would end up being the like average type of the different, or the average of the different types of gas, correct?
Okay, yeah, so the average gas mileage
Or gas, all right, yeah.
of the what? Of the what?
Of the different types of gas.
Is the same. We'll just complete this for all gas types. And then the alternate hypothesis will say that at least one of the gas types has a different average mileage. You agree?
Yep.
All right. Okay, so the decision rule, again, will compare the computed statistic to the computed to the critical or the p-value compared to the alpha. So, okay, so we clear here so far? Now, who ran this? Oh, I said we will run this using the data analysis. So does anybody have the computed F for the car type? We'll compare this with the output that we will produce using the data analysis. Shoshana, did you do this?
I didn't quite get to that part yet.
Okay. Who get to this part?
Can you show us how to do it in there without the template?
Yeah, I will. But I just want to see if anybody has at least attempted.
I got 1.39.
Which one is that, Chris? The car type?
The computed F for the car type.
Okay, what was that?
39.
39, thank you. And then the critical F?
I got 5.14.
Okay, thank you. And the p-value? This has got to be a big number. I mean, bigger than the significance level.
I got 0.319.
Okay, all right. And then for the gas type? What's the computed F for the gas type?
2.41.
Okay, thank you. And then the critical F?
4.75.
4.75, thank you. And then the p-value, again, is this a number that's going to be bigger than 0.5?
0.165.
All right, good, thank you. All right, now, so let's see how these numbers are generated using the data analysis module in Excel. All right. So we'll say data analysis, and two-factor without replication is the choice. Click OK. Input range. So what is the input range? Well, the input range, we will declare including the row names and column names. Okay, so I select this, labels. And the alpha is at 0.5, and the output range, let's put the output, let's see, maybe over here. So we're closer to the these computed values. Oops, click OK. Here's the output generated by Excel. Now, be careful though that Excel will use a different labeling for the rows and the columns, whereas I think even if you look at your textbook, this would be the treatment and this would be the rows or the blocks. So the rows in this case, the rows are the way that we declared the data. The rows are the gas types. Okay, and then the columns, the car types. So here's the, okay, let me copy this and move this. Let me just move this over to the left, closer to the numbers that you gave me. All right, so for the car type, all right, 1.39, all right, good. So 1.39, 5.14, the p-value is 0.318, good. And then the gas type, the rows, 2.41, and the computed F of 4.75, and the p-value of 0.165. Good. So what is the statistical conclusion for car type? Do we reject the null hypothesis or fail to reject? Is that correct?
Reject.
You reject.
Yes.
Look at your p-value. Remember that the null hypothesis will be rejected if the p-value is less than alpha. Look at your p-value. Quite
Okay.
high. Right? So because the p-value is quite high, the decision would be to fail to reject the null hypothesis. Same thing with gas type. The null hypothesis will also will not be rejected. Does that make sense? Was it Christopher?
Yeah, that makes sense.
Okay. Okay, and then in terms of the interpretation of the statistical results, the average mileage of the 3 cars are all equal. Okay? They're all equal because we did that for the null hypothesis. For the gas type, the average mileage of the four gas types are all equal.
So what does it mean when those results are different, like it was in the last problem?
What do you mean the results are different? What do you mean if the null hypothesis is rejected?
Well, just in comparison from the factors. So the car type would be the same, but then the gas type would be different.
No, that is, yeah, the gas type is also, in terms of the mileage, it's the same.
I'm saying, what does it mean in general if they are different from each other?
Well, that means that the, let's say, for example, for the car type, the null hypothesis was rejected, for example. That means that at least one of the 3 cars has a different average mileage, in those 3.
So it just means that if the gas was different than the car type, that the gas type affected those certain cars.
No, we're not doing that. We're not looking at this car type and gas type. We're actually testing the car type separate from the gas type. So
Okay, got it.
again, basically, here's what we're doing. For the car type, we just want to see if the mileage of the 3 cars is the same. Okay. And for the gas type, we want to see if the mileage of the 4 different gas types are the same or not.
All right, thank you.
Mm-hmm. Now, there will be times when you would want to see if there is an interaction effect, now meaning combining a car type and gas type. And so that is, if you combine a particular car with a particular type, gas type, the question is, does that produce a different mileage? For that kind of question, that goes into, I think, thank you, Shoshana, because that kind of is a segue into the next set of hypotheses, which is this 3rd set here. And in this 3rd set, we use this if we want to see if you combine a particular level of factor A and B, the question is, does that produce a result that is different from what you would expect if you took factor A or factor B separately? Okay, so you can only do that kind of analysis if you have replication, meaning that for every combination of, say, factor A and factor B, as I explained earlier in this example here, that you have replicates because for each combination of, say, gender and sector level, you have 5 observations, or otherwise known as replicates. Okay? So when you have this kind of data that is presented, there are 3 different pairs of hypotheses. The first 2, that you see here, they're the same as the two-way ANOVA without replication, meaning testing for the main effect. Because of the replication, such as these numbers, we can do this special test of what we call as interaction effect. Okay? Now, before I discuss this problem here, let me give you something that maybe all of us or some of us can relate to as far as this concept of interaction, what this interaction effect is. Okay? Let's assume that, and here's the scenario. Renee wants to study the effects of alcohol consumption and cold medicine consumption on reaction time. Okay, let's qualify this further. Renee wants to study the effects of alcohol consumption, meaning this. Let's say that the experiment is made such that this is a yes or no type of variable. Same thing with cold medicine consumption, also a yes or no. Okay, and reaction time is measured in terms of milliseconds. So in this example, you see 3 variables. What are these 3 variables? Well, you have consumption of alcohol is 1. Consumption of cold medicine is another. And then reaction time is another. Okay? Reaction time is what I want to study. So this is the response variable. Alcohol consumption is a predictor variable. So we'll call this X1. Cold medicine is another example, X2. This is qualitative. This is also qualitative. Reaction time is quantitative. So I will maybe have an experiment. Let's say that, let's see, how many students do we have in this class? Let's just say that I randomly select 8 from the class. Okay, so N is equal to 8. And these 8 individuals are Christopher, Shoshana, David, Hannah, who else? Megan, James. So 1, 2, 3, 4, 5, 6. Alan and Emiliano. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So the 8 students comprise my test subjects. So in this experiment I am going to conduct, I am going to randomly assign 2. So this one is cold medicine. And this one is alcohol. And I am going to randomly assign 2 students, of these 8, to these quadrants. Cold medicine would be yes, no, yes, and no. Okay? So let's say that, after randomly assigned, say that this one, was this, Christopher and Shoshana is assigned to this group. Say this is quadrant 1, and then David and Hannah is assigned to this quadrant 2, and then Megan and James assigned to quadrant 3. And then finally, Alan and Emiliano assigned to 4. Okay, again, the assignment is random to remove biases in the measurement. So for group 1, Chris and Shoshana, all right. Of course, if I'm doing this as a real experiment, I will have to ask, the participants' consent to be test subjects, right? So for Chris and Shoshana, I'm going to give them, maybe a shot of alcohol and then a dose of cold medicine, right? For second pair, David and Hannah, I will give them a shot of alcohol, the same one I give to Chris and Shoshana, but not give them cold medicine. Okay? And then the third pair, Megan and James, will not give them alcohol, but will give them cold medicine. And then for the fourth pair will be no alcohol, no medicine. So after I have administered, given them the test subjects, alcohol and cold medicine, maybe after 30 minutes, I will give everyone a stimulus. We'll provide some stimulus and then see how quickly or how slowly they would react to the stimulus. Okay, so do you follow the sort of the example so far? Okay, so that would be this reaction time. And this reaction time I will record for all of these 8 subjects. So this is an example of a two-way ANOVA because for each combination of, factor level, you have 2 observations. Okay? So this is a two-way ANOVA with replication. And R, the number of replicates, is equal to 2. So because this is a two-way ANOVA, we can perform 3 pairs or 3 hypotheses maybe we can answer 3 different questions. Question 1, does alcohol affect reaction time? All right? So we can set this up as HO, the average reaction time of the students who consumed alcohol. You know, I mean, this row here, going this way. Yes. Is that going to be equal to the reaction time of those who did not consume alcohol? All right. Alternately, UY is different from mu sub n. Now, I think this is something that we know for a fact what the answer will be here. If we were to conduct this test, what do you think will be the result of the test? Does alcohol affect reaction time? What do you think? Yes, right? From experience, or maybe from what we see, you know, what out there. So that's we'll call this the factor A hypothesis test. The other test would be question 2. Does consumption of cold medicine, say, you know, this cold medicine that I administer is NyQuil, does it affect reaction time? So this too would be another 1-factor test. We'll call this the factor B test. We'll set up the hypothesis as this: the average reaction time of the students who consumed NyQuil equal to the reaction time of those who did not. Translated, cold medicine does not affect reaction time. Alternate hypothesis would say that the reaction time of those who consume NyQuil is not the same as those that did not consume alcohol. Translation, consumption of cold medicine such as NyQuil affects reaction time. The third hypothesis is this: interaction effect. So the question is, does a combination of factor A level and factor B level have an interaction effect? The null hypothesis is stated this way. Null hypothesis says no interaction present. H1 will say at least one combination of factor A and B levels has an interaction effect. All right. So how does that interaction effect play into this example? what do you think will be the effect on reaction time for these two students here? And these two students consumed both alcohol and cold medicine.
It'll be even slower.
I'm sorry?
It will be even slower of a reaction.
Will be lower as if same as if they only consumed alcohol, or they only consumed cold medication, or will the reaction time be lower, much lower than either of these two?
I think it'll be even lower,
Even lower.
maybe even
Right.
asleep.
Yeah, probably, yeah, even asleep by that time, right? So that is what we, talk about in terms of interaction effect. That is, if you combine one level of factor with another factor, does that combination either worsens the value of the response variable, or it makes it better? Okay, so that's what the interaction effect is when you have a ANOVA with replication. So 3 different pairs of hypotheses. We've already seen 1 and 2. We'll see what 3 is with respect to this test. Okay? So let's apply this to this problem now. So in this problem, we have the American Association recently conducted a study to compare the weekly wages of men and women employed in either public or private sector of accounting. So you have the data. I represented the data again here, where the response variable is that weekly salary, okay, weekly wages in dollars. Okay, so this is quantitative. And the factors, there are 2 factors. The factors are X1, gender, which is qualitative. And then X2 is sector, which is also qualitative. How many factor levels are there for X1? There are 2, so male, female. And then X2, there are also 2. This is the public and private sectors. So the null hypothesis. Well, so for this one, this will involve two-way ANOVA with replication. Okay. And R, the number of replicates, is equal to 5. Okay, 5 observations in each cell. By the way, the number of replicates in each of these 4 cells must be the same. So the null hypothesis, gender. For gender, the null hypothesis would be that the average weekly salary is the same for men and women. Okay, H1, the average weekly salary is not the same for men and women. And then for the sector, I'm just going to copy this. The average weekly salary is the same for, instead of men and women, the private and public sectors. All right, and this one, not the same for private and public sectors. So that's a one-way ANOVA, one-way ANOVA. But because we have replicates, we can perform the third kind of testing, the interaction effect. All right, the null hypothesis would state that there is no interaction present. H1 says that at least one of the combinations of gender and sector has an interaction. And as far as the decision rule, again, we will compare, we will say reject HO if the computed F is greater than the critical F, or if the p-value is less than alpha. Okay, so basically the same hypotheses as well as decision rules as we have covered in the one-way ANOVA. Now let's generate the output, the ANOVA table, that will allow us to answer, to make statistical conclusions on each of these three pairs of hypotheses. Okay, I'm going to copy these and go to the template. So here's the template that we will be using. Two-way ANOVA with replication is what we will choose. Select that. And for this table, this can accommodate up to 5 observations, meaning replicates of 5. So 1, 2, 3, 4, 5, which is neat because it's the same number of replicates in the accounting example. So I'm just going to paste that data I copied. All right. So here's the data. And then this is, I believe this is public. Can somebody please confirm if I get the label correct?
That's right. Public is first and then private.
Thank you.
And then men, and men's first and then women.
Men and then women. Okay, good. So that's it. After we enter the data, we scroll down. Let me make this bigger so you can see. All right. Oh, I misspelled the men. Say men. Okay, here's the output that we will be using. Okay, so I'm not going to put this computed F and critical F because you can see that on this table, okay? So factor A is the row. In this case, it says the row. Factor A. Row. What's the row in the how we inputted the data? Gender, right? And then factor B. Factor B is the column. That's the sector. And then for the third hypothesis, interaction. So let's just pick up the p-values associated with each of these three. What's the p-value for gender, the row. Over here, do you see that? 0.0038. Okay, because the p-value is 0.0038, we will reject the null hypothesis. Okay, makes sense?
What was alpha on this problem?
I'm sorry, say that again.
What was alpha?
It's 0.5. We can set it at 0.5. Yeah, over here. Okay. So reject the null hypothesis. And then for the factor b, p-value is equal to point over here. It's not 0, but it's a very small number. So we'll just say 0.000. And the decision rule would be to reject the null hypothesis. And then for the interaction effect, the p-value is, here's the A and B. That's the interaction effect. And we pick up the p-value is 0.0672. So based on the significance level of 0.05, we will fail to reject the null hypothesis. Okay? So what are the statistical results? For gender, the average weekly salary is of men and women is not equal. Which begs the question, which gender group has a higher salary, weekly salary? To answer that question, you look at the output. Okay, look at that. The average weekly salary of men is 1,133.7, which is greater than the weekly salary for women. So we can further qualify this and say men have a higher average weekly salary than women based on this data. How about for the sector? If we look at the sector, where is that? Over here. Private sector has a higher salary, 1175, compared to the public sector. Okay, so they will copy this down. Oops. The average weekly salary of employees in the public and private sector is not equal. Private sector has a higher average weekly salary than the public sector. Okay, so far? All right, good. And then for the interaction effect, p-value is higher than the significance level. So we will say that there is no interaction between gender and sector.